Good evening students. In this video, we are going to discuss the mechanism of counter current multiplication, and we are also going to discuss how exactly loop of Henle interacts with vasa recta and collecting duct in concentration of urine, right? It's an interesting mechanism. If you understand it properly, you're really going to enjoy it, right? So let's start, right? Let's first of all draw our nephron. This is our Bowman's capsule, right? We'll draw PCT, right? And after that we will draw our descending limb of loop of Henle, right? And after that we will draw thin ascending limb. After that we will draw our thick ascending limb. After that we will draw our DCT, right? And after that we will draw our collecting duct, right? Now, counter current multiplication is one of those concepts which students don't often get when they read from the textbooks, right? For proper understanding of counter current multiplication, we need to create a hypothetical situation in which we switch off the nephron, right? After switching off the nephron, we are going to restart the whole nephron, right? Now, let's suppose we have switched off this nephron. Now we are restarting it. Now what's the osmolality of the plasma? It's roughly around 280 milliosmoles. We can take it as 300 milliosmoles, right? Let's draw glomerulus, right? So what is the osmolality of the blood which is coming through this afferent arteriole? 300 milliosmoles, right? And this 300 milliosmoles is reaching our PCT, right? But what is the typical feature of the reabsorption in PCT, right? That it's an isoosmotic reabsorption, right? That means lot of solutes are going to reabsorb in PCT, but equivalent amount of water will also be reabsorbed. So overall concentration inside PCT won't change. So when it crosses the whole of PCT and it reaches over here, we still get 300 milliosmoles, right? Now, loop of Henle, the descending limb of the loop of Henle is freely permeable to water but impermeable to solutes. The ascending limb of loop of Henle, the solutes are actively transported out, but it is impermeable to water, right? But since we have switched off the nephron and restarted it, so everywhere it is 300. Now in medullary interstitium also it is 300. It's a hypothetical situation. So in our first round, no water will go out. That means water won't go out because there is no osmotic gradient for the water to go out. So this 300 will reach over here. This 300 will reach over here. This 300 will reach over here. And what will happen over here? Over here we have got which ion channel? 1 sodium, 1 potassium and 2 chloride, right? 1 potassium and 2 chloride ion channel. So 1 sodium, 1 potassium and 2 chloride ion channel will pump the solutes inside, right? And this thing is called single effect, right? What we call it? Single effect. This is our main hero over here. This is going to drive the whole mechanism which we are talking about. Now single effect means that it is going to pump the solutes from inside the tubule into this interstitium, right? Now suppose it takes out 100 milliosmoles from here and pumps out 100. It creates the difference of around 200, right? So this will become 400, right? Now this has become 400 because it is pumped out, and this will become 200, which will go up in urine, right? 200 milliosmoles. Now in interstitium we have got 400 milliosmoles, right? Now this 300 is still coming from here, 300 is still coming from here, 300, 300, 300. Now when this 300 reaches over here, right, now we have got the osmotic gradient. So what will happen? The water will come out. The water will come out. Water will come out. And it will come out till when this also becomes 400. So this will also become 400. So this will, now this ion pump will be very happy because it is getting more solutes to pump out. Earlier it was just getting 300, now it is getting 400. Now if it extracts further 100 from this 400, right, then what it will make it? It will make it 500. Right? Now the same 300 is coming, same 300 is coming, same 300 is coming, right? Now it has got even higher gradient to compensate for. So it will release even more water, and you will keep releasing water till what point? When it becomes 500, right? So this 500 will go, this 500 will go, this 500 will reach over here. Now this ion pump will be even more happy. It has got more solutes to pump. So it will extract one more 100 from this, right? And it will make it 600, right? Same thing will happen over and over again, right? Now this water will come out. Till what point it will come out? When this itself become 600, right? And now this will extract solute from it and add to this, and this will become 700. And up to what point this will go on? This will go on up till 1200 milliosmoles. This is the maximum limit beyond which the ion pump won't be able to pump into this, right? So 1200 milliosmoles, right? So you will see a gradient 300, 400, 500, 600, 700, all the way up to 1200 milliosmoles, the renal medullary interstitium gradient. So it's actually a very intelligent design by nature, right? We have got one tube which is permeable to water but impermeable to solutes. We have got one tube in which the solutes are actively transported out but it is impermeable to water, and both these tubes kind of complement each other, right? They complement each other. So just in case if it was a straight tube, right, just in case if this would have been a straight tube, right, the gradient would not have increased above 400, right? Let me draw a straight tube over here for proper understanding. Just in case we have got a one Bauman's capsule and one straight tube, right? Suppose loop of Henle is a straight tube. Then if the ion channel pumps out, and suppose here we have got 300, inside also we have got 300, right? If ion channel pumps out 100, 400, it won't increase above 400. There is no way to increase it above 400. But when you create a loop, right, you create an osmotic gradient, right? Now this is the mechanism of counter current multiplication, right? But in kidney we have got very important mechanism called counter current exchange, right? All this medulla has got rich blood supply, right? If the blood flows randomly through this interstitium, it's going to wash out all the hard work done by loop of Henle. So nature has designed even the blood vessels in this region in a very intelligent manner, right? So what nature has done is that it has designed the blood supply in the form of loop, right? Right? So water Now this descending limb of the vasa recta, we call this blood vessel as vasa recta, right? Right? Now this vasa recta, the descending limb is going to absorb solutes and release water, right? But the ascending limb is going to release solutes, right? But absorb water, right? So the descending limb is going to absorb solutes. The solutes will go in the descending limb, right? But the ascending limb is going to release solutes, right? It is going to release solutes. And it will come back over here, right? The descending limb is going to release water. But the ascending limb is going to absorb water. So what you are seeing over here, the descending limb absorbs solutes, but the ascending limb releases solutes. So the solutes keep circulating over here. The solutes are going to keep circulating in a loop, right? But it's going to take out the excess water with itself, right? When it descends down, it is going to absorb solutes, and the concentration inside this artery will increase all the way up to 1200 milliosmoles. But when it goes up, it will start releasing solutes, right? And it will absorb water. So concentration will start decreasing, right? So this vasa recta helps in maintenance of the gradient. The loop of Henle creates the gradient, but vasa recta helps in maintenance of the gradient, maintains the gradient, right? It maintains this gradient. Right? Without this arrangement of blood vessel, all this solute will get easily washed out, right? Now, what are this thing collecting duct does in this, and why we need a gradient, right? If you just look at the loop of Henle, right, you will think that, oh, this loop of Henle is actually wasting its effort. When the solution is going inside, the water is coming out, the concentration is gradually increasing. When it's going up, the solutes are coming up, concentration is again decreasing. So here concentration increases, here concentration decreases. So it feels it has wasted its effort while going further, right? But all this effort was meant for creating this gradient. But the next question is why we need this gradient, right? We need this gradient for the collecting duct. Your collecting duct has got two portions. It has got a cortical portion and a medullary portion. The cortical portion is under the effect of ADH, right? But the medullary portion, the water is reabsorbed osmotically, right? So osmosis needs less energy, right? So we need a concentrated medulla for proper reabsorption of water in the collecting duct. So loop of Henle is doing all this hard work to create a medullary gradient for the medullary portion of the collecting duct, right? We will draw this collecting duct little to the side so that we can have some extra space, right? Okay. Okay. Now this collecting duct has got two roles when it comes to coordinating with loop of Henle and vasa recta. What are those two rules is, first of all, we'll draw a cell of collecting duct. Right, we will draw a cell of collecting duct. Right. If you follow my previous videos, you will know that ADH acts on which receptors? ADH act on V2 receptors. And these V2 receptors will act by which mechanism? They are going to increase the level of adenyl cyclase. And what adenyl cyclase will do? Adenyl cyclase will convert your ATP to cyclic AMP. Right? What cyclic AMP will do? Cyclic AMP will increase the level of protein kinase A. What protein kinase A will do? The protein kinase A will increase the recruitment of the aquaporin channels. Right? So protein kinase A will lead to recruitment of the aquaporin channels. It will recruit aquaporin 2 over here, which is going to reabsorb water. Right? AQP2. What is coming? Water is coming. And on this side, it is going to recruit aquaporin 3 and aquaporin 4. AQP3 and AQP4. And where all this water will go? This water will go through aquaporin 3 and aquaporin 4, and it will be reabsorbed into vasa recta. Right? So this is how collecting duct and vasa recta are coordinating with each other. Right? When ADH act, right, it is going to recruit aquaporin 2, the water will be reabsorbed, and it will further extravasate out of this cell with the help of aquaporin 3 and aquaporin 4, and ultimately go out through vasa recta. Right? What else protein kinase can do? Protein kinase can recruit your urea transporters, UTA1. It is going to reabsorb what? Urea. Right? Urea will be reabsorbed with the help of UTA1. Right? And all this urea, right? All this urea will go to this side of the cell, basolateral side of the cell, and will come out through which channel? UTA3. Right? UTA3. Right? And what will happen next? This, after coming out through this channel, right, it will go to your thin ascending limb of the loop of Henle. This thin ascending limb of loop of Henle, right, is permeable to solutes, but that permeability is passive, that the solute passively diffuses out, but it is impermeable to water. So it falls somewhere between descending and ascending limb. That means it is permeable to solutes, passively permeable to solutes, but impermeable to water. Right? So this urea will go through UTA1, UTA3. It will go to your thin ascending limb, right? And what will happen after that? This urea is going to circulate, right? It will go to your DCT, it will go to your collecting duct, it will go to, again come over here to UTA1, UTA3, thin ascending limb, and this cycle of urea will go on. This cycle, this big cycle of urea will go on. Now why we need this cycle, right? Because urea contributes roughly like 40% to this medullary osmolarity, right? We need urea over here because urea contributes 40% to medullary osmolarity. In many urea transporters defect, right, the subject loses the ability to concentrate urine. If subject loses the ability to concentrate urine, they are going to excrete lot of water, and this will lead to hypotension, right? So urea contributes 40% to renal medullary osmolarity. Okay. So this is how your collecting duct, by reabsorbing water and reabsorbing urea, coordinates with your loop of Henle and vasa recta, right? Now what things can go wrong? Now we understand the whole mechanism, right? Ultimately, why we are reading this? Because we know that where the things can go wrong in this, right? One major syndrome in which the things can go wrong in this Bartter syndrome. The Bartter syndrome is going to paralyze your 1 sodium 1 potassium 2 chloride, right? So the single effect will be lost. If single effect is lost, the kidney will lose the ability of counter current multiplication. So there won't be enough of medullary interstitium osmolarity, and kidney will lose its ability to concentrate urine, right? So in Bartter syndrome, you get a lot of hypotonic urine. Okay, this will get blocked, right? What else can go wrong in this, right? If you see this loop, of vasa recta, right? It's a long loop, you can see, right? The flow is sluggish inside this loop, right? Flow is sluggish inside the loop, and the osmolarity is very high, right? Flow is sluggish, osmolarity is very high. Since the flow is sluggish, that means oxygen also has got lot of time to dissipate. So you got the combination of three things: sluggish flow, high osmolarity, and hypoxia. These three things are going to dehydrate the RBCs inside. If these RBCs become dehydrated, and if there is any genetic defect of sickle cell, so there is high probability of sickling of RBCs in the vasa recta. So the vaso-occlusive crisis of sickle cell anemia can be precipitated because of this long loop of vasa recta, right? If you have the sickle cell trait, right? So in vasa recta you can have vaso-occlusive crisis of sickle cell, right? Which will ultimately lead to necrosis of medulla, right? Okay. Now, what else can go wrong over here, right? Now, let's first of all see. Now, what are the things that are affecting this concentration mechanism, right? First thing is that the longer is the loop of Henle, right? Longer is the loop of Henle, more will be the osmotic gradient, right? So we can safely say that osmotic gradient, right? Let's write in short form. Osmotic gradient is directly proportional to length of the loop of Henle, right? Other thing which we can safely say, that osmotic gradient is directly proportional to this single effect, right? The strength of the single effect. More is the single effect, more this ion channel pump is working, the more will be the osmotic gradient. So we can say our osmotic gradient is directly proportional to single effect, right? Other thing is, more sluggish is the flow, more time this ion channel will get to absorb your solutes, right? So one thing we can say that osmotic gradient is inversely proportional to the flow rate, right? More sluggish is the flow, more time the single effect will get to reabsorb the solutes, and more pronounced will be your counter current multiplication, right? So osmotic gradient is inversely proportional to the flow rate. Right? So these few things you need to understand. It is directly proportional to the length of the loop. More length is the loop. That's why juxtamedullary nephrons have higher concentrating ability. Right? More is the single effect, more will be the osmotic gradient. Less is the flow rate, more will be the osmotic gradient. Right? What else can go wrong in this? Right? Another thing which can go wrong is not directly related to this, but what is the ion channels over here? One sodium, one chloride, right? So sodium chloride symporter, right? This gets affected in which syndrome? The Gitelman's syndrome, right? This can also affect your medullary osmotic gradient. Gitelman's syndrome. Minor effect, but yes, Gitelman's syndrome. And suppose the ADH is acting but the V2 receptors are defective. If V2 receptors are defective, then what it will lead to? Your nephrogenic diabetes insipidus, right? Nephrogenic DI. I'll write it nephro DI. Right? Suppose someone is on lithium drugs, then this aquaporin 2 will get down regulated, right? So in case of lithium toxicity, there will be down regulation of aquaporin 2 channels, right? And this will also ultimately lead to your nephrogenic diabetes insipidus, right? And there are many drugs which act on V2 receptors. Some are V2 receptor agonists and some are V2 receptors antagonist, like desmopressin. Desmopressin is your V2 receptors agonist, right? So if something has got V2 receptor agonist, that means what? More aquaporin 2 channels will be recruited and more water will be reabsorbed and you will get less urine, right? So you can use these kinds of drugs for nocturnal enuresis. Drugs like desmopressin, right? Desmopressin is going to work as V2 agonist. Right? Now, there are many conditions in which we want the patient to urinate a lot more, right? Be it hypertension, many other conditions. So, in those conditions, we are going to inhibit this V2 receptor, right? For inhibiting this V2 receptor, right, we are going to give the drugs like convaptan and tolvaptan, right? So convaptan and tolvaptan are going to block this V2 receptor. Right? And just in case, in urea transporter defects, right, the medullary interstitium, the osmolality of medullary interstitium will fall down, right, and the subject won't be able to concentrate urine, right, and it will lead to excess urine output, right, which will ultimately lead to hypotension, right. So for summing out everything, right, we need what to say, loop of Henle, right, and DCT and collecting duct and vasa recta, and all these structures interact with each other for concentration of urine, right? For proper understanding of counter current multiplication, right? We switched off the nephron, then switched on the nephron all over again, right? This 300 will go, and since it is our first round, no water will come out, right? And once this 300 reaches over here, the solute will be pumped out with the help of 1 sodium, 1 potassium, 2 chloride, right? This will become 400. Now this 400 will absorb water from the osmolarity, right? The 300 osmolar fluid coming through the PCT, right? So this will also become 400, right? Now this cycle is going to repeat, and the osmolarity is going to multiply repeatedly, right? Your loop of Henle is going to create the gradient, the vasa recta is going to maintain the gradient, and your collecting duct is going to use the gradient, right? And we also discussed in detail the various syndromes and various drugs which are going to affect the overall situation, right? So hopefully this video has helped you in understanding the counter current multiplication, the counter current exchange, the urea cycle, and all the drugs and disorders involved in the whole scenario, right? Wish you all the very best. Thank you.